the foundation of place value. It's so critical for so many reasons. But the most immediate reason for us now is how it is used to develop thinking about addition. I used to have a video of a student working on a problem. It was a three-digit adding situation, and you saw the role that place value plays in that. So let's suppose now that place value is really a powerful way of thinking, and students are now thinking about addition. Let's think about how this can play out. But first, I want you to try something with me. You gotta really do this. You might have to pause the video and try this. I'm gonna ask you to close your eyes, and then I'm gonna ask you to double the number 38. Like in your mind's eye. Don't write it down. Just in your mind's eye, double 38. You can pause the video now and think about that for a minute. I'll be quiet because you're pausing the video. All right. Did you do it? Did you double 38? Now, when I've done this in live audiences before, most of the time, people do not perform what we would call the standard algorithm. The standard algorithm is where let me show you, where you do something like this. You always start on the right, because when you add, you always go from right to left, and you go 8 plus 8 is 16, then you carry the 1, and then you add 1 plus 3, and you get a total of 7, you get 76. Sometimes people do that in their mind's eye. They close their eyes, I say double 38, and they kind of run through that standard algorithm, but it's pretty rare. It's much more common for people to do one of these things. See if you did one of these things. They close their eyes, they think 38 plus 38, and they actually see 30 and 30 is 60, and then 8 and 8 is 16, and then 30 and 16, um, 60, let me try that again. 30 and 30 is 60, 8 and 8 is 16, and 60 and 16 combine to make 76. As you do that mental math, most people start with the 30 and 30. They don't start with the 8 and the 8. Or another strategy, people will do, let's see, 38, double it. That's 38 and 38. Well, 38 is really close to 40. So I'm going to do 40 and 40. That would be 80. But I know I didn't have 40, I had 38. So I'm going to back off 2, back off 2. So 80, back off 2, 78, back off 2, 76. So they actually do some rounding and adjusting in their head when they do this. They do 40 and 40 is 80 and then back off to get 76. And then sometimes people literally will double. They'll go 38 times 2. And in their mind's eye, when they go 38 times 2, then depending on their thinking, they might do the standard algorithm. 2 times 8 is 16, 2 times 3 is 60, 60, 16, 76. Or sometimes they'll do double 30, like I said before, is 60, and then double 8 is 16. Put those together, you get your 76. Here's the point. I hope you thought through this, and I hope you maybe were able to think about this in several ways. But the idea is this. The standard algorithm is not necessarily the most flexible or fluent way to think about this situation. So that's not how we naturally think, is the standard algorithm. The standard algorithm is taught, and then we might use it because we were taught it and we got good at it at some point in our lives. But the standard algorithm is not what's natural for us to think about when we're just pressed to do something like double 38. In fact, the standard algorithm, this whole like carrying the one thing, that only emerged historically because back when we had only, feather pens and ink bottles, and people were doing their accounting for their businesses, paper and ink were not readily available. And so if you could squeeze all your computations into the littlest amount of space using the least amount of paper and the least amount of ink, that was beneficial. And so 38 plus 38 and carrying the 1 allowed you to use less ink than if you had written, say, 30 plus 30 is 60, 8 plus 8 is 16, 60 plus 16 is 76. That would take more space and more ink. So the brain doesn't naturally think that way, the standard algorithm. It was a man-made thing for efficiencies historically. And so what I want you to think about as we move forward is how can we leverage students' natural thinking as they engage in addition problems? All right, let me first of all give you some theory. We're going to talk about algorithms. The standard algorithm I mentioned before. Well, what is an algorithm? An algorithm is a step-by-step, finite step-by-step procedure for accomplishing a task. For example, we do algorithms all the time in math. Multi-digit addition, subtraction, multiplication, and division. Do you remember long division? We'll get to that later, but long division, or sometimes there's an algorithm for converting from decimals to percents, or there's algorithms for adding, subtracting, multiplying, dividing fractions, for computing averages, whatever the case may be. There are so many algorithms in math. And often that's the problem is students learn these algorithms like this without deep, well-connected understanding that might actually go against their nature. And so what we want to do is leverage the nature so that algorithms make sense so that students can understand and actually use them correctly, precisely, accurately, fluently, efficiently. And so I have a learning theory. To engage in this, we have to have our students think about meaning. And if we're going to start with addition, say, we have to start with what does it mean to add? Students have to have in their brain a conceptual understanding of what addition or subtraction or multiplication or division means. And then, of course, they have to have a good way of thinking about place value. Then, I believe, we need to put students in situations where they have to engage in reasoning and problem solving. There has to be a problem to solve. It's much more motivating and interesting when students have something to think about in terms of a context of a problem that they can actually solve. And then they initially can do it with hands-on manipulatives. Now, in this online class, we're going to be using virtual manipulatives, as you've already seen. But imagine in the classroom with hands-on manipulatives. And we're going to transition from hands-on manipulatives to drawings to ultimately written algorithms. And then finally, we're going to push for generalization. How can we look at the work that we're doing, the thinking that we're engaged in, and generalize our procedures, our algorithms, to lead to this computational understanding? All right, I'm going to take you through a cycle of this with addition, and it looks like this. First of all, what shall we mean by addition? Now, pause the video, and I'd like you to write down your thoughts. If somebody came up to you on the street and said, hey, what does it mean to add? What do you mean when you guys here in America say addition? What does that even mean? Will you pause for a minute and brainstorm some thoughts? Addition. What do we mean by addition? Here's how I would phrase it. Addition is when you have more than one quantity. Maybe you said number, value. I think quantity is the better word. You have a quantity of something and you have more than one. Maybe you have two or three or four, but let's just say I have two hands. I'll use two for now. Addition is when you take the two quantities and combine them to produce a new total quantity, a sum, we call it in math, right? Addition is when we take two quantities or more and combine them to create a new total sum quantity. All right, so with that understanding of addition, combining of quantities, let's try a problem. On Friday night, 167 people attended the school play. On Saturday night, 285 people attended the play. How many people watched the play altogether? Do you feel the essence of addition here? There's 167 people on Friday night. There's 285 people on Saturday night, and we want to combine those two quantities to get a grand total of how many people watched the play. Now, forget about these pictures for a minute. We're going to jump to the manipulatives. Now, I hope you still. So this link with the base 10 blocks, get it out and play along here. In fact, we'll have you pause the video and try it. But first, Remember, we're adding quantities, combining quantities. The first quantity is 167, and we're going to combine it with 285. Hey, will you pause the video and try it? But as you do, pay attention to your thinking. How are you approaching this? What are you doing? Why are you doing it? Be prepared to just think that through. Maybe write some notes about what you're thinking as you engage in this. Pause the video. All right. I don't know what you did, but I've done this with live audiences, hundreds of times, and with adults in MAT256 and with kids. And I'm making this up, but I'm just going to say 99.9% of the time, here's what happens. When students are going to combine these two quantities and thus add, they usually do this. They go to the big ones first. They go, I have this 100, I'm going to combine it with this 200, and they're going to say, I have at least 300 people who went to this show. Then they move to these blocks and they start combining quantities and they go, let's see, down here we have 2, 4, 6, 8, we have 80, 90. There's another 100, and they'll take this group of 100 and move it over to here, and then keep combining. Now we've got 1, 2, 3, 440, and then they go to the small ones and they start combining. So we had 5, 6, 7, 8, 9, 10. Oh, we've got another 10. So they'll grab those 10 and move it over to the 10s. And so now we've got 1, 2, 3, 410, 20, 30, 40, 52. They'll say we have 452 people that went to the play. Yeah, it's most common. It's nature for most people in my experience. I don't have a research study to back this up, but based on my observations over the many years, kids, adults usually start with the big manipulatives, push them together first, then the next, and you can see it happen here. 452. All right, now we would do this for a while with kids for days. They would have manipulative, they'd have problems to solve, try to get things that they're interested in and have them push together, but then record what they did. Eventually, we want them to record what happened here, and I'm going to try to do that with the drawing tool here. But if I was to record what I did, and maybe yours would be a little different, but if I could record it, here's what I did. I had 167, and I added 285. Now remember, at this stage in the game, our kids don't have an algorithm that was the efficient historic algorithm. What they have are these meanings. They know what addition means, they know about place value, and we're just exploring some things. And so to record it, maybe they would do this. Well, the first thing I did is I took the 100 and I combined it with the 200, and those together gave me 300. Then the next thing I did is I took the 60s and I broke them apart into 10s and I added them with the 80s, and I took two of them, which left me with 40, and I combined them with the 80, and this group of 80 plus 10 plus 10 gave me another 100. So now I was up to 400. But remember, I still had the 40 left down here. So far I had 440, and then I had 7 and 5, and I took the 7 and broke it up, and I took 5 of the 7, leaving me 2, and I combined them with the 5 that were over here, and 5 plus 5 gave me 10, and so I took that 10 and I moved it over here to this 40 to actually make that a 50, and then I saw 452. Now, you guys, I'm trying to maybe exaggerate a little bit here, but when you ask kids to keep track, to record their thinking, in combining those two quantities, it sometimes looks like a mess like this. And maybe right now you're like, oh my gosh, but that's okay. We have to leverage the kids' natural inquisitiveness, their natural curiosity, and their natural way of thinking. If you just ramrod down their throat the standard algorithm, that's when math becomes, I don't understand. Why do you put that little one up there? I don't understand why you're making me to do this thing. Help them to get there, but start with what's natural, and it might look a little messy, and that's okay. Now, what I would do then is continue through this, give them new problems every day, or several new problems every day with manipulatives, and as they record their work, you might challenge them. Can you record your work in a neater, more efficient way? And we start working on that. And over time, I'll share with you what it looks like over time. But over time, it gets a little bit neater, a little more efficient, a little more organized. And student thinking is the center of it all. All right. So I hope you've had that opportunity to try that. But now I want you to see what it looks like with kids. We now maybe transition to, rather that one day they walk in the room and there's no manipulatives. And instead of manipulatives, they start drawing it out. They're drawing squares, they're drawing the tens, they're drawing the ones, and they're combining them together. And they're still combining the hundreds first, and then the tens, and then the ones, and they're pushing it all together, but they're doing it with drawings. But then, as efficiency becomes more efficiency with different problems, here's how it might look. Suppose the problem was 167 plus 25. That's what we had, right? Now, what students naturally do is start with the big blocks. I had 100 blocks and 200 blocks. I had 300 blocks. Then I had 6 tens and 8 tens. And 6 tens and 8 tens gave me 14 tens, 140. And then I had 7 and 5, which gave me 12. And so if I start combining this, I have 300, I have 440, I have 340, 50, I have 352, I have 452. Look at that work. It's beautiful and it's good. And you might be wondering, but wait, that's not right. They went left to right. It's okay to go left to right. We don't have ink. We don't have a shortage of paper. Let them work left to right. It's fine. All right, then sometimes it's not as neat as that. And this is a scary moment for teachers sometimes, is that you're letting kids think, you're leveraging their natural inquisitiveness and curiosity, and you're letting them record their own thinking, and you're watching for that, and you don't know what you're going to see sometimes. But let's say a student did this. Hey, will you pause and think about this for a minute? And then you can listen to me talk about it. So imagine you were watching your students work and they're working on organizing their work and they're trying to be more efficient. And this student writes 167 plus 285, and then he writes these little dashed lines to kind of separate the place values. And then this is what this student did. He saw 100 plus 200 is 300. And then he saw this as 60 and 8, and he wrote it here. He saw with his manipulatives that he had 14 tens. And he knew. Now this isn't the first thing, the first way it looked. It probably looked messy like mine initially, but then after a while it got less messy. And this kid said, I had 14 tens, but I took 10 of those tens and I moved them over to the hundreds column, leaving me just the 4 tens. And then over here, I had 7 and 5. That was 12 singles, but I clumped together 10 of those singles and I moved them over to add another group of 10 to the 4 to give me 5. And so when it was all done, I had 452. Isn't that nice? This student is essentially recording the carrying of the one very meaningfully. And it's connected to their work that they had done. They literally had manipulatives on the floor where they were grouping together groups of 10 and moving them to the new place value. And this student is showcasing that as connected to their kinesthetic experience. They're showing that bundling and moving over, and they're kind of doing a carry the one. Beautiful. I have one more for you. Pause the video. Take a look at this one. Now this student did. Now this is again after a while, and I have to tell you, I have interviewed so many kids over the years. Sometimes kids think about stuff when they're not just mimicking what the teacher told them to do. When the kids are given freedom to think and reason, they think and reason. And so here's what this kid did. 167 plus 285, and he just thought, that's too hard. I'm going to make the 167 170. But if I, like in his brain, the way he said it was, I took 3 of the people from Saturday night and I moved them to Friday night. So now I have 282 here and 170 here. Okay. Then I took 30 people from Saturday night, 252, and I moved them to Friday night to 200. Like, why are you doing this? Because when I get to 200 and 252, 452 just pops out. Now, this is after some work. This was what happened after some iterations of, hey, could you do it more efficiently? It might have had several more rounds. Like maybe he was moving 2 people at a time or 3 people at a time. But as he worked on efficiency, he moved 3, then he moved 30, and then he was able to do the sum very quickly in his head. Hey, if I had students in my high school and college classes that were able to think mentally about mathematics like this, that would be fantastic. Instead of, as soon as they have a 3-digit addition problem, mine gets turned off, grab a calculator and start pushing buttons. This is really good thinking. I hope you agree. All right, I'm going to pause there. That's enough of a start with whole number algorithms. We'll have you do some more exploration with that in subsequent modules, but I hope that gets you off to a good start about allowing students to think, leveraging their natural inquisitiveness and curiosity and creativity, and building from manipulatives to drawings to abstract representations that get more and more and more efficient. They go from really not efficient and unorganized, and they move towards efficiency and organization. Hey, engage early, engage often, and stay in touch.